Alright, so that's the first method we have of creating an assembly language program for the Mattel Aquarius and running it on the Aquarius or the emulator. And the process itself is quite straightforward, quite simple, although it took a long time to explain all the technical details that we need to understand in order to do it. But now that we know those technical details, let's go on to our next method for creating and running a machine code program for the Mattel Aquarius, which is going to be this one here, the basic loader method. And you can see my note here says is for an unexpanded Aquarius. This one, it doesn't require the micro expander module or the micro expander functionality to be enabled in the AquaLite emulator. And this is actually very similar to a method I described for loading a machine code program into a Sinclair Spectrum computer in a previous video, but I'll go through it again. And essentially what we're going to do using this method is we're going to look up the bytes of code for our machine code program instructions, and we're going to use this basic loader program to load them into memory, and then we're going to execute them the same way that we did before using our USR instruction, which should be here somewhere, right here in line 140. There's a bit of a sneak preview. You see we're going to be using this USR function again, but this time we're going to be using it a little differently in that we're actually going to be passing a parameter into this USR function, which we'll see in a moment. So let's go ahead and go through this program line by line so we understand it. Again, probably I wouldn't use this method for creating and running a machine code program on the Aquarius because it involves looking up the individual codes for each assembly language instruction, which we wouldn't want to do. We'd probably just want to use an assembler. But I'm just going to include this method here because it's another kind of quick and dirty method we can use, and it might give us some more insight and understanding into the process in general. So here, let's go ahead and take a look at this program. And the first line of this program here, line 100, go sub 1000. So let's take a look at line 1000, which is right here. And it's a REM statement saying that this is the machine code loader part of this program. So the first line of this program, it simply prints character 11, which is the clear screen character. So it clears the screen, as we can see right here. If I can get these text to line up here. If we look at the notes over on the right side here, we see line 1000 is a REM statement. And then line 1005, print character 11, which clears the screen. And then line 1010 here, it's an input statement. It simply says machine code starting address, and it asks the user to input an address where we want our machine code program to start in memory. And again, we're using this AD variable. So this will allow the user to input a memory address where we want our machine code program to live. And here we see our two familiar lines of code that we used previously, where we're extracting both the high and low bytes of the address that we just entered. So it takes this AD variable address and breaks it down into its high and low bytes. And we're going to use that again to poke the system variable for the USR function. Right here, we're going to be poking address 14340 and 14341 to tell the Aquarius USR function where our machine code program lives in memory so it can execute it. And then in our next line of code here, we're reading our machine code program. So before we get into the section that reads our machine code program, let's just jump down here to the end where we have some lines of data. So in this method, I'm actually storing both the assembly language and machine code program in this program in the form of data, in data lines. So here we have line 2000 is a data statement, and the first part of this data line is a string variable, which is just a string that shows me what assembly language instruction is that we're going to be converting in our program. So this is simply a string that tells us that the first instruction in our assembly language program is call 166 decimal or 682 hexadecimal. So this first instruction, which I'll explain a bit more later, is going to call a ROM routine that is built into the Aquarius computer. So this first data element is a string which just tells us what the assembly language instruction is. And then the second element is a number that tells the computer how many bytes of data are included in this instruction. This particular instruction takes 3 bytes of machine code in order to execute, and then it's followed by those 3 bytes, which are right here, 205, 130, and 6. So this assembly language instruction call 1666 breaks down into machine code bytes 205, 130, and 6. So the first line of our program is going to call a ROM routine, and we'll talk about later what exactly that does. So the next line of our program here, in this second data statement, it says LDHL 12288. Well, that 12288 value should be familiar to us now. It's the first character position in that hidden line of characters at the top of the screen. So this memory address will contain a character that will show up not only in the top left corner of the screen, but also it will fill the entire border with this character as well, which is what we want this program to do. And again, the next number tells us how many bytes of machine code this instruction takes. In this case, this instruction takes 3 bytes of data, which are 33, 0, and 48. So those are the machine code bytes that make up this LDHL 12288 instruction. Okay, let's take a look at our next data statement here, which says LDHL in brackets, comma, E. So let's explain what this instruction does now. We're going to learn a little bit more about the Aquarius, and specifically about that USR instruction that runs our machine code program. So here what we're doing is, you can see we're loading a value into a memory location. So the memory location is specified by this HL register pair, which we now know from the previous line up here has been loaded with a value of 12288. So we're loading a value into the memory location 12288, and we know that that location prints a character on the screen and also fills the border. But what value are we loading into that location? Well, here you can see we're loading whatever value is in the E register into that memory location. So remember, in our previous example, we put a value of 25 into that memory address because 25 is the code for that little robot symbol that we printed on the screen. But now we're loading a value that's in the E register. Well, we didn't load anything into the E register to begin with, did we? So how do we know what value this is going to be? Well, we're going to take a look at that in a moment. So let's just finish off this part of the program here. And you can see this load HL, comma E instruction takes 1 byte of data, which is this value here, 115. So load HL in brackets, comma E converts into the machine code instruction value 115. And then finally at the end here, we simply have our return instruction, which contains 1 byte of data, which is a value of 201. All right, so now let's go back up to our program and learn a bit more about how this works. So remember, the first line up here, it go subbed line 1000, which is right here, which is our machine code loader program. And we printed character 11, which clears the screen. And then we input the machine code starting address and put it into a variable called AD, which is the same variable we used last time. We broke down that 16-bit address into its low and high bytes right here, high byte, low byte, and we poked those values, low and high, into this system variable that tells the USR function where to find our machine code program. And now here we are at line 1060, and we're reading the data that we just took a look at in these data statements. So the first thing what we do is we simply read the string, which is a string telling us what assembly language instruction we're dealing with, and it puts that into this variable B string. And then it also reads this variable N, which is the number of bytes of data in that particular assembly language instruction. And then in line 1070 here, we print characters 10, which simply moves the cursor down to the next line to create a blank line on the screen. And then we print B string, which is the assembly language instruction that we just read from our string in our data statement here. And then here we have a for next loop for LP, or loop, equals 1 to n. So we know that n is the number of bytes in this particular assembly language instruction, and we're going to create a loop for each assembly language instruction that contains however many bytes that particular assembly language instruction breaks down to in machine code. So for example, our first instruction here, call 1666, contains 3 bytes in machine code, which are 205, 130, and 6. So this loop is simply going to read each of those bytes one at a time. It's going to cycle from 1 to 3 in this case because there are 3 bytes in this instruction. And it's going to read the byte here in line 1090, read BT. It's going to read this machine code byte and put it into a variable called BT. And then it's going to poke the variable AD address, which is the address where our machine code program is going to live, with that byte. And then it's going to print AD, which is the address, along with the contents of that address right here, peak AD. So it's going to read the byte of data, it's going to poke it into memory, it's going to print it on the screen along with the address so we can see what the address has been poked with. And then our next line of code says if BT equals 201, then return. So it's looking for this 201 return machine code instruction in our data, and if it finds that code, it knows that it's reached our last byte of data, which is a return statement in this case, and then it will return out of this subroutine. Otherwise, if it doesn't find that return instruction with a value of 201, it falls down here to line 1130, which increments our address pointer, AD equals AD plus 1, and then it finally increments our loop counter right here at next LP, and it cycles through again, getting the next byte of data, loading it into memory, and then displaying it on the screen for us. And then finally down here 1150, we have a go-to statement that goes way back up here to 1060 to read our next assembly language instruction. And that's simply what this section of code here does. It simply loops through all of our data down here in our data statements, reading the string of the assembly language instruction, reading all the bytes of data for the machine code, and then manually poking them into memory locations. So you can see obviously the drawback in using this method is we have to know what the machine code bytes of data are that represent a particular assembly language instruction. And we can find that out, for example, by looking at a very handy website called Z80 Heaven, which I'll just bring over here. You can see here we have Z80 Heaven, and this is the opcode reference chart. And if you scroll down, you can see that this chart shows all of these Z80 assembly language instructions. For example, if you want to look up a particular instruction, like let's say I look at my program here and I want to look up an assembly language instruction here like LD brackets HL comma E, for example. So here if I go back to my chart and I press Control F for search, and then I type in LD space open bracket HL close bracket comma, and you can see stuff highlighting in the chart down below there, comma E, and here we are right here. So our instruction is right here, LD HL in brackets comma E, and the code for this instruction is 7.3 in hexadecimal. And if I go back to my calculator and I select hexadecimal and I convert 7.3 into decimal, you can see here the decimal equivalent for hexadecimal 73 is 115. And if I go back to my program now, you can see that's the value that I have here in my program, 115, because that's the machine code byte for the assembly language instruction LD brackets HL comma E. So this method is kind of tedious and clunky. You have to look up all of the values yourself rather than assembling it, but it does work. And so we can go back up here to our top part of the program here after this go sub instruction where we read all the bytes, and we'll see what's next. So the next thing is we're again printing characters 10, which is a carriage return. And then the next line here says input value to pass to machine code routine semicolon V. So this is a new feature we're going to discuss now, which is this USR function here, which is actually executing our machine code program. It can take a value that we pass it and put that into the machine code routine for us as well. So another feature of this USR function is we can pass it a value in the brackets here. And you can see in this case, we're passing it a value that happens to be located in a variable called V. And what value do we have in V? Well, in line 110 here, we have an input statement where the user actually enters a value for this V variable. So the user is going to be asked to enter a value, and this value will be passed to this USR function, which is executing our machine code program. And then the next line here simply prints a message on the screen, press a key to run machine code, and then in line 130 here, we simply wait for a key press. If in keys equals nothing, then 130, then it just simply loops back to this line 130 over and over again until a key is pressed, and then it drops down here to this USR instruction, x equals USR V. So this time it's again going to execute our machine code program, but it's going to execute our program being given this value of V that we've passed into it. And how does this V value get used? Well, if we go back down to our program here and we take a look at what our program does, you can see that here we're loading the HL address with a value that's in the E register. So what happens is when we give this USR function a parameter that we pass to it inside these brackets, if you look at my note here, it says call machine code program, and it says the value in brackets is passed to the DE register as assigned 16-bit value minus 32768 to 32767. X will contain the value of DE. So I think how this works is, or how it seems to work is, whatever number you pass to the USR function inside the brackets here, that gets passed into our machine code program in the DE register pair, and then our program can use that value in the DE register pair to do whatever it wants. So in our particular case, you can see here, our program is using the value that's in the E register. Since we're only passing it an 8-bit value here, we're entering a number that goes into V, because this number is going to represent a character to be printed on the screen. So this time, instead of printing that character 25, which is the robot, we're going to allow the user to enter the value of a character that they want to print on the screen. And then our machine code routine is going to take that value that has been passed to it in the USR function, which ends up in this DE register pair, or in this case the E register, because we're only going to be passing it an 8-bit value. And we take that value and we poke that value into this memory location, which corresponds to the address on the screen, which gets printed in the border and on the top left corner. So that's kind of cool. We can actually pass values to our machine code subroutine through this USR function. But one thing we have to take note of now is this last, or rather first, assembly language instruction, call 166 decimal or call 682 hexadecimal. So what does this subroutine do? Well, to be honest, I don't actually know what this subroutine does, other than it seems to allow us to pass a value to the USR subroutine in the DE register pair. So I don't know exactly how it all works. I'm just going to show you the ROM disassembly once again, and we'll look for this address here. So we're calling address 682 hexadecimal. So if we go back and take a look at the ROM disassembly again, and we'll look for this address 682. All right, so here is our ROM disassembly, and let's look for address 682 in hexadecimal, which is right here. So you see here is address 682. And so the first line of our assembly language program calls a subroutine in the computer ROM memory that lives at this address 682. So if you want, you can try and go through these instructions and see exactly how this works. These are the instructions that this particular subroutine in the ROM, or this ROM routine, executes. Again, I'm not sure how it works. I think it might have something to do with the DE register pair, because it allows us to pass a value into our machine code program in the DE register pair. So in order for us to be able to pass a value to our machine code program in the DE register pair, we need to call this ROM routine at address 1666, which is why this instruction is here. So let's go ahead and run this program now in our emulator. And remember, this one does not require the micro expander module. So it says here basic loader method for the unexpanded Aquarius. So I'm just going to leave my emulator in this regular Aquarius mode without enabling the micro expander functionality. And I'll press enter, and then I'll copy my program, Control C, and then Control V to paste it in my emulator. just like that. Now if I run this program, it asks me for a starting address where I want to save my machine code program. And again, since this is an unexpanded Aquarius, I'll save it at address 16,000, just like we did before. And now it prints the different assembly language instructions for me on the screen, as well as the different addresses where our machine code bytes are stored, and it shows us what those bytes are. So if we go back to our program here, we can see the first instruction, which is that call instruction, should be made up of bytes 205, 130, and 6. So if we take a look at our program here, we can see that our first instruction here, which is our call instruction, is indeed made up of bytes 205, 130, and 6. So back in our emulator, it just simply shows us all the different assembly language instructions and their associated machine code bytes, along with which memory addresses they're stored in. And of course, our final instruction here is the 201 return instruction at address 16007. And then it says value to pass to machine code routine. So we need to choose a value to pass into that machine code subroutine. So again, if we pass the value 25 into it, we would expect our program to fill the border with that little robot character. So let's just try that. We'll try using value 25, and I'll press enter, and we'll see what happens. Oh, now it's asking us to press a key to run the machine code routine. So now I'll press a key and it'll run our machine code program. And there we go. It works exactly the same way our program in the first example worked. It puts this little robot character into the first character display memory location, which is 12288, which also fills the entire border with this character, just as we would expect. Only this time we used some different functionality by passing this value into the machine code routine instead of hard coding that value into our assembly language program. And we could run the program again and give it a different value. And let's see, what value do we want to give it? Well, let's check our manual again. And we'll find a different symbol. Maybe this little man symbol here at character 140. So why don't we try that one? We'll type run. Starting address 16,000. Value to pass 140, which will be our little man character. Press a key to run machine code. And there we have the border filled with our little man character this time. So this is another method we can use for creating and running a machine code program on the Aquarius. But this one is, like I said, more tedious because we have to actually look up the different machine code bytes that make up our assembly language instructions. Alright, so now we've learned two methods for creating and running machine code programs on the Aquarius. One is a lot simpler than the other one. And now I'm just going to briefly actually touch on another method that you may run across for creating machine code programs for the Aquarius, just so you have some exposure to it in case you run across it in your travels, and I'll let you know how it worked out for me.